Okay, so before the break, we started our discussion on logic, and there's a whole lot of talking there. So I'm going to move half of that talking back to next week because we did plenty enough lecture time on Monday. So let's jump over to a little side thing to cover.
Sorry,
those will involve examples. I'm kind of assuming here everybody knows what the normal playing cards are. I know we have a couple students who aren't natively from America. Yeah, I guess it's generally unlikely that we have Native Americans in the class, right? The Indiana is traditionally Miami tribe, and Miami, when the American settlers arrived, the Miami tribe mostly just moved into the villages with them. Not a big population percentage in Indiana, or even often distinguished. So I'm just going to say American, but some people aren't immigrated here from elsewhere. So traditional thing in bunch of little paper cards with pictures drawn on them. Some of them have face cards. We have different symbols, 4 sets of symbols with cards numbering 1 to 10, and a couple with pictures of faces on them, and 4 different categories. I assume everybody's familiar with those. I grabbed those out to point to them. Traditional gaming thing. I have electronic versions, but I was planning on using one of the other computers. So I did not download them to my Windows machine today. So let me grab some digital version. Let me grab a digital version of playing cards for our example so that we can use those today. And then we'll get into our example. Which I send these out in like every single semester. If I go into the files from every semester that I've taught, I could find the folder of a copy of these. So here's pictures of playing cards. These came from the American Bridge Club. I can pull up what it is real quick. Pictures of playing cards. Some bridge club. Well, I don't see it on here now. Bridge playing cards. Yeah. So some bridge club that they just went ahead and made their pictures of cards free for anybody in the world that wants to use them. So I've been using their pictures in classes. There's a thing about them we'll talk about here in a second that makes them really useful for programming their version. So obviously they have them because people programming a bridge game for the club. Oh, I can't get to my new announcement button. It's behind the Zoom pictures or thumbnails. There are some images, playing cards for class example. What is today? 4/13. Okay, so y'all should have those playing cards to use for our example. You'll sound, don't know from Ivy Learn. They have a really nice naming pattern that there's a setup to where it makes it easy to program with those pictures. So we'll get to that here in just a second. Because, well, one of the things about card games is they're randomized, right? We take our cards and kind of do this without, well, and mix them up. I'll have to do it this way to be on the camera. We randomize the order, and then people playing the game pick one of the cards. So in this case, a 6 of clubs, or pick another card, 4 of diamonds, 8 of hearts, and we consider it randomized. There is a finite number of orders, sequences that we can put cards in, but it's not a number that we would ever consider finite. It's 52 factorial. So it's bigger than the number of atoms in the solar system. There's lots and lots of sequences they can go in. So for our intents and purposes, it's random, which makes it a great example for this topic as far as software development and programming goes. Random numbers. I'm saying values, because, well, the computer does random numbers, but, well, as you probably already can easily guess from the fact that I just sent you a bunch of playing cards, it's not necessarily the number that we want. We're going to do something else with that number. So sometimes our software requires values to be randomly chosen at runtime. Change things up a bit. Several of y'all did this in that guess a number game. A couple people jumped ahead on that first one. There's that one was supposed to be where there's like just a couple of guesses. That first one, you set the number, and then maybe the user has 3 guesses, and you copy and paste your if else selection structure several times to duplicate those guesses. And that way, when we get to loops next Monday, loops seem much more appealing than all that copy and paste stuff. But some people jumped ahead and did that. But I know when I came to school to get the computer paperwork, it was because I'd been using computers for decades at that point and didn't have any paperwork. So, and that's certainly not an uncommon reason to be in programs like this. So a lot of people already know programming and jumped ahead a little bit. So that was nice to see. Some even went ahead and used random numbers. But I wanted to make sure and talk about them specifically, because now that we can make choices, a lot of times we want our software to do different things, and those choices are going to be based off random numbers. A random number so it's different every time. And it's random as far as like the cards in the deck. That's why I like this example, because technically that is not random, right? There's a it's very deterministic when we start mixing up the order, the sequence we end up with, right? But it's random enough. We're not going to sit there and do that calculation. So there are 2 types of uncertainty like that. 2 types of uncertainty. So the first one is like the deck of cards. That's epistemic uncertainty, which is the definition on that is uncertain due to a lack of knowledge. Kind of like the cards I just mentioned. It is completely deterministic when we start to shuffle a deck, the sequence that we end up with in the end is completely deterministic, but we're not going to do that calculation, right? It's we're not going to have knowledge about it, so it's going to seem random for all intents and purposes. The example I put here was a coin toss. That's even simpler than shuffling the deck of cards, because when we flip a coin, it's either going to be heads or tails. And technically, it's fully deterministic. That is fully deterministic by the laws of physics. Laws of physics. But that's only a technicality, because the laws of physics and causation, how hard that coin was flipped, the air resistance, other events in the universe where that coin was flipped at, all of those things come into place. So we're never actually going to succeed at doing that calculation, which means it's random enough that if we need a one or the other choice of flipping a coin is usually a good option. It's random enough for our purposes. The other type is aleatory. Which this is true uncertainty. That's an R. There's absolutely no way to know beforehand. An example of that would be radioactive decay. The laws of physics only give us a probability that an atom is going to decay. For a particular atom, I should say that. The best we can do is the probability that an atom will decay. We don't have any foresight into the details. We don't know what time a particular atom will decay. We know that one is going to, but there's no way to predict which one. Right? We know that one is in a certain amount of time, say from a chunk of uranium, in a given amount of time, so many atoms are going to decay. It depends on how many are there. So we could take those same atoms, cut our sample in half, and then we have to recalculate everything. But we can't say anything about a particular atom. We have no idea when a particular one will decay. But we can give the probability for every single one. And we know it's going to happen to the accuracy that's what our clocks are based off of. We base our clocks off that. We know it's going to happen, but we can't make that final prediction. Best we can do is probability. It's truly random. So obviously machines only follow patterns. So the truly random stuff's off the table. So machines do the epistemic sort of random. Epistemic patterns will be close enough for our purposes. Kind of like shuffling a deck of cards or flipping a coin. It's random enough for the purposes we need. It's often referred to as pseudo-random or just the illusion of being random. So a couple of vocabulary terms there that you probably get by without knowing. I just want to make
Probable chance, like on drop rates in a video game, like something has a percentage to be an ultra rare drop. What about that type of randomness?
that is still epistemic. Because
Okay.
that's the kind we can do. The machine can make it very complicated, sort of random, but it is still predictable. Kind of like
Reduce the chances
cards.
even more.
Yeah.
Okay.
It's epistemic. The sequence we get when we shuffle it, there's a finite number, but that number is more than the number of atoms in our solar system.
True.
So it might as well be random. We'll never predict the exact one. And these are just the technical terms for that. Since this is a college class, I like to include the technical terms, the proper vocabulary. Aleatory randomness, which we certainly can't do in a machine because all we can do is follow patterns. So there's no way our pattern could be truly random. Our patterns have to be epistemic, which is a big fancy word. So we just go ahead and say random because it's random enough. It gives the illusion of being random. So random values in a machine. Values in a machine are probabilities with minus the certainty. Probabilities except for certainty. And by certainty, that means 100% chance. So we look at a probability, which the two ends of our spectrum for probability that never occurs, 0% chance, no possibility of happening, versus absolute certain that it happens, or 100% chance. We don't want that certainty. So we take out the exact 1.0. So basically a random number, I'll just write R here on the board. But again, when we go to put this in the code here in about 5 minutes, because it's 1 page of notes. R is going to be between 0 and 1, including 0, but not 1. So we always have that. And then the number we want can be manipulated into a different range. Into I'll say desired range. So we always have this probability minus the certainty. We don't want to deal with 100% when we're looking at random numbers. And just some number between 0 and 1. So a floating point number, 0 point something, 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 for as many bits as the computer is running on has. And then we can manipulate it into our desired range. And most programming languages have this part built in, pre-built functions for manipulating to the range we want. If you only work in one programming language, that's fine, because one thing about that is there's no standard for what to call those manipulations. So we ask for them in different ways in just about all of our languages, which makes a whole bunch of things makes a long list of things that it's hard to remember, and they might be close to each other but slightly different. So it lends itself to typos. So frankly, I've found it's a lot easier just to go back to this base one and manipulate that every time than trying to remember the particular syntax of how we get the, like, say 20 integers in a particular language, because that's slightly different everywhere and creates a long list of things to remember, where this one is pretty much always the same, or this one is always the same, and expanding it is easy. For example, a 20-sided dice. Usually in classes like this, it's safe to assume that people are familiar with D&D, right? Dungeons and Dragons. Most people in the IT courses most people have played at least one round of D&D. So familiar with 20-sided dice. So if we wanted to turn this number, some number between 0 and 1, into a 20-sided dice, well, there are two options. Option 1 would just be kind of divide by 20. R divided by 20. And we split that out down into this range into 20 sections. So our pseudocode would look something like, if R is bigger than 0.95, then I don't know, then it's a 20. If it's not bigger, there is R bigger than 0.9, in which case it's a 19. Otherwise, else if R is bigger than 0.85, then 18, and hopefully y'all can see where that pattern's going, right? We divide by 20, and that's 0.05 each time. So we just section that out in a selection structure, or we could do some math with it. And a lot of people find it a little bit easier to turn that into an integer to work with. So option 2 is we take that random number and turn that into an integer just by doing a little bit of math on it. So we have this range 0 to 1. So R is between 0 and 1. If we multiply by 20, then we get something, well, 0 times 20 is 0. The random number is still a random number. So random number between 0 and 20 times 1 gives us 20. So that gets us from 0 up to 19.9999999. However many nines our particular machine can hold in its register size. 32 bits or 64 bits, but a whole bunch of 19.9999 in there. So not quite 20, and actually a little more than 20 integers, right? Then what we can do is we floor that number. 0 is already dropped down, truncated down to the next lowest integer, so that's still a 0. The random number is still a random number in there. It's just an integer now, because floor cuts off all the floating point part and just leaves the integer section behind. And that slightly smaller than 20, the 19.9999999 stuff, well, that drops down to 19, and we get that equality there, because we do have exactly 19 there. So that gives us 20 integers to work with. And in the case of like a dice, if we were doing a D&D game, I'm really surprised I didn't see anybody put that in their projects. That's one I see almost every time I teach this class. Somebody wants to make a D&D game. I'm like, yeah, that's perfect for this class. If we add 1, then our random number is between 1 and 20, or a representation of that 20-sided die, like we would think of for playing a game of Dungeons and Dragons. So that manipulation part is really easy, because this is basically what we do every time. we need a floating point number, we just don't do this step. But we just multiply it by something to make it bigger. Or we divide it up into the sections we want. Most humans find it easier to work with the integers though. We just multiply it by the size you want. And then floor it, truncate off the floating point portion. So we get back to integers, and then we have the appropriate number of integers. So that's what we can do for to simulate a deck of cards here for our example. So okay, if I erase this side. And that's what we always have. So it's really easy to do the manipulations. And I found it's a whole lot easier to do the manipulations than try to remember the syntax for all of them in a whole bunch of different languages. Because another thing is we very rarely work in only one programming languages. Most languages have different strengths and weaknesses. So we mix and match which ones do which part in order to get the optimal thing for our situation. We virtually never work in just a single programming language at a time across the field. That's pretty much never done. So we mix and match them, which means we often have to remember various syntaxes. And if we can make that list shorter, it makes it a little easier with the things we have, because straight memorization is hard. So for a deck of cards, and I also like to use this example because there's a little subtlety that makes that can make this tremendously easy, easier. It can make it tremendously easier, but it might not be obvious at first how we get that. So we need 52 numbers. So we'll start with a random number, generate a random number between 0 and 1. It doesn't include 1. And then we'll multiply that by 52. Gets us a random number between 0 and 52. And then if we floor that number, we get a random number between 0 and 51, or 52 values that we can then use to find our number. And I guess I ran out to find our card. So this will be our card. And then we just have to associate that number with one of our cards. And there's a nice little trick for a deck of cards that makes it a whole lot easier, but may not be your first intuition. So I would like to show this. So as a good example of look for the little tricks. Sometimes it's worth it to take a couple minutes and think about, are there any little tricks that would make this easier? So this is kind of lead into that. It's okay if I erase the 20-sided die thing. Hopefully that's very easy. And yeah, I was kind of surprised. I think this is the first time that there hasn't been a project proposal of somebody wanting to make a D&D game. So if anybody has yet to turn that in and is trying to come up with a project, those are great projects for this class. So once we have our number, we need to split it up into our normal traditional American deck of cards where we have 4 suits. 52 cards are organized into 4 suits, spades, hearts, diamonds, and clubs. And then we have 13 values of each, which our technical term for that is ranks. So we need a quick way to divide things up this way. Our ones are referred to as aces, and then 11, 12, and 13 have pictures on them. That's the royal cards, a jack, a queen, and a king for each one of our suits, in case anybody's not familiar with those cards. So one thing we could do is just go through and assign all those directly. That's probably what your instincts are, right? 0 is the ace of spades, 1's the ace, 2 of spades, 3 is the 4 of diamonds, 4 is the 7 of clubs and go through and do an assignment for each one. But there's a nice little trick that shortens this, because we need to turn 51. We have some number between 0 and 51, and we need to turn that into two numbers where we have 4 values and 13 values. And we can get there directly by dividing. So our biggest number is 51. So I'll put our biggest one here. And well, then we could divide by either one. I'll just put the 13 here. So 51 divided by 13 will go up to 3 times with 12 left over. Right, that has to be our biggest remainder, because anything else would have been another multiple of 13. So if we divide that, the total quantity we have, by one of our categorization values, we find 4 things and 12 things. Because when we divide, then our quotient or just write a Q. Sorry, I've been using algebraic notation for this section, so I'll just stick with that. So our quotient is some number between 0 and 3, which is 4 values, right? 0, 1, 2, 3. So that gets us our 4 suits. Four values to represent our suit. And our remainder is going to be somewhere between 0 and 12, which we started at 0, so that's 13 values to represent our rank. So instead of doing all those assignments, all we have to do is divide our number and then just check where the placement is. The other little trick, though, is we started at 0. So if we started going through our deck of cards and started with an ace, then I'll start with spades. So 0 represents the spades, and the second number, remainder 0, would represent the ace. Then 1 would represent the 2, and 3 would represent the 4, and we're off by 1, right? But we can quickly fix that by simply making 0 the king. Because our intuition is going to try to start with number 1, and we go 1 through 13, but it corresponds to 0 to 12. So if we move that number 13 back in the 0 spot, every other number lines up perfectly, and we don't have to do any other thought about it. And you see there's a nice little trick that really shortens the work of all assignment for each particular card. And then we can just do a selection structure, right? If our quotient is a 0, it's a spades. If it's a 1, it's a heart. Then we just do definitions. So like 0 is spades, 1 is a heart, 2 is a diamond, and 3 is a club. Kings are 0, which actually works out, because if we had our 13th card, what's 13 divided by 13? Or our 14th card would be the king here. Somewhere in there, when we get to the new suit, I kind of lost track of the language there. When we get to the new suit, our quotient goes up by 1. Our very last one has a remainder of 0. Yeah, 13 divided by 13 would be 1 with a remainder of 0. So that 13th card is where 0 is the remainder. So it still lines up. It just probably a little counter to the intuition, because our intuition is going to tell us to start at number 1, not at number 13. Do you have anything else there? Oh yeah, and then jacks and queens are 11 and 12, but that the way we normally sort the order of playing cards, that falls right in place. So do quotient and remainder division and make zeros king, and then we have places for all our cards. So let's do this in an example. Go ahead and
I think
share
the
my
trickiest
screen.
thing is remembering the 0 is being a placeholder as well, instead of just disregarding 0.
Yes, we start at 0. There's a reason for that. We'll talk about the reason why computers start at 0, not at 1, when we get to when we talk about arrays, because there's a discrepancy. 0 is our first thing, but as humans, our intuition tells us 1 should be first, right? We use the same symbol for those, so it seems like 1 and first should align, but they don't. When we ask for something versus when we count something is different in machines, and we'll talk about that in detail soon. So we're not going to see graphics in Python this semester. It's a little more complicated there, so we'll go through this in Raptor, but logically it will logically the same thing will happen. It's just we're not going to see graphics in Python, so we will need to I guess to do the same thing in Python. The logic would be the same, just in text instead of pictures, instead of flowchart symbols, and the you'd have to spit out words instead of show the picture. But the nice thing about this is notice the naming pattern we have here. So like our 2 of clubs is 2C, 2D, 2H, 2S, or when we get down to 5s, 5 of clubs is 5C, 5D, 5H, 5S. So if you look at that for a second, you'll notice there's a really nice naming pattern to work with. And whenever you're going to work with images, like a big set of images like this, you want to make sure that naming pattern's in place. Some sort of pattern you can work with. Because we can easily build up that string, right? The first part is our quotient. Or sorry, the way I wrote it on the board, the first part is our remainder. And then the second part is a letter that corresponds to our quotient. And then we immediately have the file name of all these images. Oh, then we just have to add the .ping at the end. So go ahead and open up Raptor. Oh, the computer's running slow. There we go. And I'm going to make a subchart to do this first, to pick a card and apply this logic, and then we'll grab the images. So I'm going to put it on a subchart, that way we can do it twice, and like, I guess almost like a game, draw 2 high cards, and one of the cards is going to be higher than the other, right? So I'll call this pick a card, give it a nice meaningful name. And what we're going to do is choose a random number and then do that stuff that's written on the board. So I'll put that in a variable called card, things we've seen before. The new part is what we're assigning to that variable. And I'm going to work from the inside out. We saw that in text the other day. Things going left to right, top to bottom. That's how we work in English. But we're not working in English here, right? We're working in programming languages. So that's the final result, but it's probably not going to be the order our mind thinks about it in. So the first thing we need is a random number, which in Python is just the word random. Actually, I'll run this much so you can see what that does. Pick a card. And you see that gives us a random number somewhere between 0 and 1. If I run it again, we get a different random number. And obviously, every time we do this, we get a different number. So that gives us a way to, that's sort of a random number. But we want that to represent a card. So we need to do those things written on the board. We don't want any random number. It'd be hard to work with the floating points to figure out where we need to split our section, our 0 to 1 up to get 52 values. So it's a lot easier for humans to work with integers. So we'll multiply by 52, and then we have a random number between 0 and 51.9999999. So now I'll wrap that all in parentheses. And I got my cursor back to the beginning by using the home key. If you're doing stuff on computers, you probably never use that in your, before coming and starting an IT program, but you're going to want to get very familiar with your home and end keys on the keyboard. They are incredibly useful. And they're in a different spot on every keyboard. So that's going to be one of the first things you're going to want to get used to. Look for every time you get a new keyboard. One of the first things you're going to want to look at if you're in IT is where are the home and end keys. The home and end keys move the cursor around. So let me jump over to a text editor so I can make it bigger. Oh, in the delete folder, I'll call this card thing. Make the text a little bit bigger. Here's some random text. Oh, which in Python we might have indented text. Here's some indented text. So wherever the cursor is, if you push end, it goes to the end. Same thing up here. If I just hit end, it goes to the end of the key, the line, or home goes to the beginning of the line. Here, end of the line or the beginning of the line. And if it's indented, so this is something that'll be very useful in Python. Notice if I hit home again, it just toggles back and forth across that tab area. So useful to highlight things. Like if you want to highlight that whole line before the days of before the days of having a mouse, when we needed to highlight stuff, we'd hold shift and use the arrow keys. So if you want to highlight a whole line, you can just put your cursor anywhere on it. And if you hit end to go to the end and then hold shift and hit home, it'll highlight that whole line. And then if you repeatedly hit home, it'll toggle back and forth between that indented area. That's a very useful thing. I like to show keyboard shortcuts because we usually have well over 100 buttons on a keyboard, but a mouse has maybe 6 at the most. So we have way more control with the 100 buttons than we do with the 6 buttons, usually 2 or 3. So that's a good way to get the cursor at the beginning, is that gives us a random number between 0 and 51.9999999. So if we floor that, then we have a random integer somewhere between 0 and 51. So 0 or 22, 22 again. Yeah, there's not a huge number of them there, but it gives us a random number in the range we're looking for. Then we can do those 2 assignments to find out our rank and suit. So our rank, there's 13 ranks. So that would be the remainder if we divide by 13, which that's what our modulus operator gives us. So if we take that card, mod 13, we'll have some random value between 0 and 12. And to get our suit, we'll take that card and divide by 13, which this is floating point division. So that that will give us the decimal value, but we want the integer here. We just want the quotient. So again, I'll wrap that in parentheses. So my cursor is at the end. So I'm gonna go ahead and put that closing parenthesis, and then I'll go to the beginning and floor that back to give the open and do the opening parentheses. So then whatever, after doing that division, just discard the floating point portion. So we have an integer again. That gives us our rank and suit so that we can build up the name, the card names we need. Put them over here. So from where this file is located, the file path to the other one is into a folder called PNG, and then follows that nice naming pattern. So I need to build that up as a string, and I'm going to build it up in several steps. Thus far, every time we needed a string, we built it up in one box. But usually, if we're going to build one up, it can be a whole lot easier and easier to work with, especially if something goes wrong and we need to fix stuff, if we do it in multiple steps. So I'm going to start by, so the file path to the image we want, I'll create a variable called file path. And the first part of that is from where we're at, we need to go in that folder PNG, and then a slash, and then we need the card name. It might have been a good idea to rename those cards, but that's the first part of where we find that file. And the next part requires a selection structure. That's why this falls into this week's example. Because now we can do that check over here. There's only so many things we could have, right? So the first thing we could check and see if our suit is equal to 0.
Right now we're creating a card game, aren't we?
Yep.
No.
So if our suit's equal to 0, well, then our file path gets some stuff added to it. Our file path is going to get whatever was already there, because that was the first part of the string, but then we're going to concatenate on a little bit more. Because if it's a 0, then we want maybe spades.
Well, how'd you get those cards? You know, how'd you get those? You just downloaded them?
Yes, I sent those out to you. They're in Ivy Learn.
Okay.
If you go to Ivy Learn, there's an announcement that has the pictures of the cards.
Yeah, I think I got it. I just, just looked over it like real quick, and then I just, glimpsed at it, but didn't like see there was a link down there. But
Okay.
Other than that,
yeah. So then all of our spades would have an S from that pattern, which is the second part of that. So we actually need to do another one of our rank first. So we have our number, and then so it goes rank suit. So I'll do another selection first. And if our rank, well, it could be a 0. And well, we did this one earlier. If it's a 0, then that means we have a king, which here we can see the kings are KC for the king of clubs, KD, KH, KS. So when we put the file name together, set file path, oops. We're going to take whatever is stored in file path. So we want to refer to that variable directly, because we're going to add more stuff to it. So what was already stored there plus a K for king. So that if our number is 0, 0, if our random number is 0, then we get the king of spades. So it do that selection structure, 0, it adds a K to it, another 0, so then it adds an S to the end of the string. And then we just need to add the .png at the end for the file to finish the name of that file. So file path is going to be the path that we've already built up plus .png for the file type. And now we have a way to actually ask for that. Does that make sense? Now we just need a whole bunch of copy and paste our selection structures. So I'll copy this one, paste it in there. This one. So our suits, if it's not a 0, is it a 1? If it's not a 1, is it a 2? And that's everything we have to check. Because if we divide our biggest number, which is a 51, by 13, the largest quotient we could get is 3. Because 4 times 13 is 32, or sorry, 4 times 13 is 52. So that's bigger than the number we're looking for. So if 0 is spades, maybe 1 could be hearts, 2 clubs, and if it's none of those, I'll copy this one, click over here where I want to go, and the only thing left it could be is diamonds. So, and then it'll add the file type at the end there. Now we need to do the same thing with our rank, but it's a little bit easier. So I'll copy that once. So I selected the whole thing, that we add the assignment block in there and everything. So if our rank's not a 0, which again was our remainder, it could be a 1. And if it's a 1, we want an ace. I'll paste that in again because the next few are kind of easy. If it's not a 0 or a 1, is it a 2? And because if it's a 2, then our file name just has the digit that we found. So we can add that digit right onto the string. And we do that all the way up to 10. And then for our other ones, jacks, which would be 11, we put on a J, and queens would be 12. The 12th rank we'll put on a Q. So this one's going to be a lot of copy and paste. That might be good for an else statement, because there's only a couple really special cases, right? All we have is the kings, queens, jacks, and aces are our special cases. And then the rest of them we could do all at once. I just used FilePath. The question in the chat room about why I chose FilePath, because that's what we're looking for. I want to draw that image. That's why we're doing it in Raptor, not in Python, so we can draw the image of the card instead of just put a word on the screen. So what I want is not because we could do the same thing and spell out a sentence like that's the jack of clubs or something using the same selection, but we have images, so it's nice to see images when we can. So all we really have to worry about is our special cases, which is 0, 1, 2 through 10 is the number exactly. So I guess the next one we really have to check would be 11. We don't have to check anything specific till we get up to 11, which would be a jack. Paste in another one. And we do need to check 12.
So you keep copying and pasting the selection.
Yes, but now we're done because we checked all our special cases and the rest of them, it gets the digit.
Could you maximize the window, see what it looks like?
I don't think it's all going to fit. I could try making it a little smaller.
Yeah, let's try it.
Can you see all of it there?
Yeah, sure. I'm just gonna try to probably take screenshots of it. I got the screenshot
Okay,
here. So
screenshot's a good way to do it.
yeah, just go up a little bit and wait, are we done with the whole thing? Is that
A question just popped up in chat room. I don't get why you didn't add 3 to 10. So 3 to 10 are special cases. So we did 0, 1, then jumped all the way to 11 and 12 because 2 through 10, we need the number directly. So we can do that in our else part. I skipped it to answer the question in the chat. I skipped those in order to condense this, make it as short as possible. Yeah, so here, our file path just gets that number. Whoops, we'll set the file path to what the file path already was, plus whatever number we found. And then once we have that part, so that's the first part of the name. We add the second part of our name on, then do the file extension. So now we should have the place to find those image files if we run this. Yeah, so we go in that folder and look for 5c.ping, which is one of our cards.
Hold up, let me screenshot this. Hold up.
Oh, there's going to be more coming. I'm going to share this after class, Keegan. I'm going to send this one out when we're done.
Could you share the images of it?
You already have I already sent you the images.
Oh, okay. Oh, of the screenshots here that for the cards.
The cards.
Raptor?
Yeah, I already sent you the file of cards.
Yeah, I know, but I meant the screenshot of like the Raptor.
Oh, I was going to send you the actual Raptor file.
Ooh, nice.
That'll be easier than screenshots, probably. Make sure you copy it, right? You don't just look at it, like use it for reference and copy and paste over.
Okay.
And then the chat room asked about the last part. So the last part just added .png. Because we do have to tell the computer what sort of file that is. But now that's an image, right? And we saw what to do with images when we looked at graphics. We can call some pre-built code. Oh, wait, I need a selection structure first. Do an assignment and say, I'll call it card pick is assigned to load bitmap, and loading bitmap just needs that file path. Oh, this is why I named it file path, because I thought the little predictive text was going to say file path here, but it says file name. But hopefully you see those are the same. I was trying to match the predictive text it was going to pull up, is why I really chose file path, but I forgot this says file name, not file path. We can load in that image, and then we can put that on a scene. Well, I'll do this up here. I'll open open graph window. We need some sort of size for it. I don't know, 500 by 500 is probably good. And things we saw before, with the pictures of cards, it seems appropriate to have a green background. So I'll clear the window back to green. That just seems like the appropriate color for a card. Then we have a card. So now we should be ready to just display that card on there. Display bitmap. Oh, draw bitmap. And what bitmap? Well, that's going to be card pick. And where do we want it? So our windows, where's my little pen? So our window sketches can be helpful here, just like we saw before. So our window is 500 by 500. Whoops, that's supposed to be a 0. 500 by 500. So if we do it like a game, put one card here and another card here, so we can compare them. I don't know, maybe 40 pixels over will work. And then we can come up. We can come up a lot. 4,400 seems like a nice numbers. Oh, my pen stopped working. Come over 40 and up 400. That'll fit on our screen. And then we can make our card like 60 wide and 120 tall or something. See, a little sketch can help with the graphics, putting those together. But it's just sort of an idea. It's still just a guess. So I'll come 40 in the X direction, then 400 in the upward direction, and then make the playing card like 60 pixels wide and 120 pixels tall. Maybe 100 pixels tall. That might be good. Sort of a random guess to see what it looks like. So if we run this, there's our graph window and the color, and it steps through picking the card in the background, that whole selection structure. Oh, and it found that 47 divided by 13 would be 3 with a remainder of 9. No, 3 with a remainder of 8. 3 times 13 is 39. We have left 8 left over to get to 47. And then we were able to build up a string and put that image on there. It looks like that card could be bigger. And the placement looks good if we're going to make it a little bit bigger. Oh, that is right here. So maybe it could be like 90 wide and 150 tall. I'll turn the speed up so it goes quicker. That'll work. And then we can pick another card so that we can compare them, right? So again, copy and paste. Because humans make typos, machines don't. Copy and paste and use predictive text and things like that as much as possible, because we're the ones that makes typos. Let's see. So our original card was at 4,400. So we probably want it to be at the same height. Well, actually, we could bring it down so it looks like it's a different side of the table. It's 90 tall, so we'd plenty of room if we go 150 up. But we need to go further over, and it's 90 wide. So 40 plus 90 would be 130. We probably want a little more space. So I'll just go to 30. Really, that's a random number. I started to do some math, but yeah, somewhere around further over in the screen. So that should give us 2 cards. And then we have like a pick a high card thing. Player 1 and player 2, or you could quickly add some stuff to turn that into a game thing. The main takeaway from this example which I meant to end 8 minutes ago. So this wasn't quite as short as what I initially planned. But our main takeaway is random numbers, because we'll need those sometimes. That's our syntax here. I better show the random numbers in Python if you want to do it that way, but we're not going to look at graphics in Python. It's a little more complicated there. And you kind of have to have a local installation of Python. So we'd have to install and configure the language and stuff. So we won't see those in this class, but I can show random numbers real quick. So how we get a random number, and manipulating that would look exactly the same in Python. We just cast it into an integer in Python. So it's like int does the same thing as floor. Then we can use this trick to build up a string. So if it's just like text-based output in Python, you would probably spell out the words based off the same selection structures. And then once you get the word together, you're ready to do something with it. In our case here, we drew a picture. The word we put together was the name of a file and where to find it. So then we just drew a picture of it, and yeah, copy and paste that 5 times. Then you have like a hand for a game of poker or something. It could be a typo. There's a question there, so we'll deal with questions in just a second. I want to quickly show the syntax for this in Python. I think I have idle on here. So in Python, if we want a random number, we have to include a library that's not there by default. I was going to look at it in just a second, Johnny. I was going to see if we have you share your screen, and then we'll go over the process. So in Python, to do this same thing, we need to import this library called random.
Kind of like importing time.
Import random.
Okay.
And then a random number is from that library. The library is like a whole collection of things. Then we use a dot to get to the stuff in that collection. One of those things is random with a capital R. So if we do that, that gives us a random number. Oh, whoops, with a lowercase r. Let me try that again. We have a random with a capital R and a random with a lowercase r. We want the one with the lowercase r. So random.random, all lowercase, and then put some parentheses at the end, and that gives you a random number. Random.random. This time I'm going to copy that, so I'll fix that typo. Random.random, and then I'll use Shift and Home to highlight so I can copy it and paste it in here, and you can see that's given us that random number between 0 and 1. So then we just multiply that up and turn it back into an integer to do the same thing we just did over here in Raptor. But the big difference there is you'll want to build a nice grammatically correct sentence about your card, because we're not going to see graphics in Python. There's too many things we'd have to do that would take up time we don't really have here. So you said you were having a problem, Johnny, with it not finding your card. Can you share your screen with me real quick? And then we'll kind of look at the problems if you were following along. Because that's another thing. When I go through an example that was practiced ahead of time and do the stuff, it's a lot easier to find. Oh, so ping is that folder was in ping. The first part of our file name needs to be the folder name. Can you pull up the File Explorer? Yeah. So we need to go into that folder. Is your Raptor file saved at the same spot as the folder? Where was your Raptor file saved? Because
Sorry. It'll be easier.
Oh.
I'll look at where the Raptor's probably in the.
oh yeah, anytime you want to unmute, just there's no such thing as an interruption in a Zoom call. Just unmute and interrupt me, because that's what works.
Yeah, it's right here. It's the
Okay,
card.
so we need our file to be right next to it. So copy that entire PNG folder with all the images over here, or take your cards to downloads. Either way would work.
I got so much stuff. So
Oh, where is the extracted version of that file?
unzip it.
Oh yeah, you'll want to unzip it. Yeah, Zoom slows that down quite a bit.
Yeah. And then I can.
Yeah, and then inside of that, because it has all that extra stuff there, that's the one we want. So if you just copy that folder over to the same place where your,
Which was, I think, documents. Yeah, and then can I just paste it in?
paste it right here. Yeah, so that's relative addressing. We,
Okay, yeah.
whenever we write a program, we can use the file path relative to where we're at. Like we can go up and down folders. Down folders is a whole lot easier than up, and just navigate from our program to that file. But going the other way, or if it's in a completely different location, we might need to use the absolute address. So like on a Windows machine, we'd start at C:/users/documents and the whole entire file path. Oh, so the first part is the folder name. So the first part is capital PNG. If we look over at the watch window there on the left,
This one.
yeah, so that's the extension at the end, and it looks like you added that.
Okay, so it should not have the dot. It should just be like this.
Yes.
Okay.
So
And then this one should be .png, like it's an
Yeah.
extension.
so it might be better to rename that folder as cards or
Yeah.
something. That would be less confusing. The first part is the folder name, because we're going to go into that folder.
And then this is the like pulling up the .png.
Yeah, and then that's the one that's actually ping. That's the extension that tells us it's an image. So now you want to run it and give it a try? That part looks good.
Let's hope.
We got the numbers, built the string. Oh, it's still building the string.
Oh, perfect. There you go. Perfect. Now,
The name of the cards does have a capital C. You might want to watch that.
yeah.
Windows is not case specific, but on Raptor doesn't work on a Mac.
It
On a
says
Linux
error.
system, it would make a difference.
Yeah, I caught the uncapitalization, but I was like, whatever, I gotta write all this stuff really fast so I don't get left behind. But yeah, okay, thank you.
Yeah, the biggest place that's gonna come into play is when you start doing web stuff, because most of our websites are hosted on Linux servers, which is case sensitive, and most of us work on Windows or Mac machines, which by default anymore, Mac turns case sensitivity off.
Okay.
So Windows and Mac don't care whether we have uppercase or lowercase letters, but that Linux server that we're going to put our website on will. So it'll lose track of all the files and stuff. So it's a good habit to form to just go ahead and watch case sensitivity along the way.
Okay. Thank you.
Any other questions for people following along? I'm going to send you that file so you can copy it and mess around with it some. And whenever I send out the files like that, if you were just listening through the lecture, and it's an active subject, so make sure you do the stuff, because it's a very active subject. We learn by doing. So doing is that's why we have the class examples, and I'm going to send that out right afterwards here, so you can do that or pull the video back up. It'll be rendered down in a few minutes and follow along. And that's a useful thing, kind of leads right into a card game, a very natural thing. Or alternatively, if you don't want to do the pictures, you can build a string the same way. Your string doesn't have to be a FilePath. You could just have a grammatically correct sentence that says something like, your card is the 8 of hearts, or your card is the 9 of spades, the jack of clubs, and just build a sentence that way. It might actually be good practice to do both if you're just starting out here, right? Find the picture and display a sentence to say what it is to get some extra little practice, because it's an active subject we learn by doing. So now is a good time to go do stuff. Does anybody have any questions before we kind of split off for the day?
Nope, not me. It looks good. Oh, one more thing on the import. Does that refer back to when you were telling me to import time for the Python project I was doing with the light?
Yes.
Okay.
So
Making connections.
Python has lots and lots of libraries that are available, but it would be a huge load on memory if we had them all at once.
That's
So
true.
only some base features are there, and the rest of them are off to the side that we have to ask for them as we need them.
Okay. Thank you.
And we can add more. Anything we write, we can then import in, so we don't have to. So import just brings in already written Python.
Make it more
code.
modular.
Yes.
Yeah. Okay.
Exactly. Any other questions? I already counted down from 5, so I assume no. So I guess that'll be it for today. You all have a great weekend. If you have any questions for the next hour and 10 minutes, our scheduled time, I'll be sitting right here by the computer, and we'll be able to jump back on a Zoom call in a split second to address questions. Please use our time productively. I can answer more IT questions than just this class. Questions about our class need to come first, but I am able to answer more questions than just for this class. So if you have any, let me know. That's what I'm doing for the next hour and 10 minutes, is waiting for you all to ask me questions. Otherwise, you all have a great weekend, and I will see you on Monday.
Oh yeah, so I got a question for the